All right. So just as a way of review here, we're solving exponential equations, and exponential equations, when you're asked to solve these, you have a variable in the power. Okay, so a variable in the power. We have two methods for doing this. One is same bases. That's what the first one is up here. Get the bases to match. The other is use logarithms. Take the log of each side. Okay. Then we're also going to do these logarithmic equations, which require us to use the properties of logarithms to join them together as a single logarithm and then solve. All right, 1 and 4 are parallel problems, so I think I'm going to do 1 and 4 together. Number 1, I can rewrite the 27 as 3 cubed, right? And when you have a power to the power, you can multiply. So this is 3 to the 3x equals 3 to the x plus 1. And when the bases match, as they do in this case, you can set the powers equal. So 3x equals x plus 1. If I solve that for x, subtract the x over, divide by 2, I get x equals 1/2. And we are going to need to check our values when we get in these logarithmic ones, but it doesn't hurt to check it. Plug in 1/2. That one's not so easy to check. 27 to the 1/2 equals 3 to the 1.5, but they are equivalent. Right, so number 1 and number 4 are actually parallel problems, okay? Believe it or not. Let's go ahead and do 4 next. I'm going to rewrite number 4 so that I have log base 4 of x to the second equals log base 4 of 9. So I'm moving this 2 from a product of the log to the exponent on the argument. Now, this is also the method of same bases, believe it or not. Do you see the bases are the same here?
Yes.
Those are same bases here and here. So if those match, you can say x squared equals 9. Now, this brings up an interesting problem here. It is, when I solve this algebraically, I get plus or minus 3, but not both of those works, right? So algebraically, I get x equals plus or minus 3, but only x equals 3 works. Here's why. If I plug in -3 on the left-hand side here, I would get an error message. It's not in the domain. Remember, the domain of logarithms is written up here. The argument x has to be strictly greater than 0. So the -3 will not work when I go to plug it in. And we're going to find that there are some values that we get on a couple of these problems that won't work. Okay, they're extraneous solutions. All right, number 2, if you see an exponential equation as simple as this, all it has is one base, an exponent, and an answer or argument, you can go straight to the change of base formula. The change of base formula applies to this. Also, what I would recommend is, let's get away from log base 10. You probably did that a lot last year. Let's just use ln. Okay, get used to using ln. You'll use that more often anyways as you move on in math. So, according to the change of base property, what would x equal in this one? Just doing so well here. What would x equal here? If I change it to ln, I'm going to have ln over ln. And it's always ln of the argument. What's the argument or answer here? 7 is the argument or answer. Think of the argument as the answer. And then over ln of the 3, yeah, on the bottom is a 3 because that is the base, yeah. It does not matter. You can do log of any base you want. But once again, you know, certain calculators all we have is the option of ln or log base 10. But you can do any base you want. As a matter of fact, that 23 on the homework, we changed it to log base 2 just to suit our purposes for simplifying it without a calculator. We never actually plugged in log base 2 to the calculator because things canceled out, right? You can use log, you can change it log any base you want. So now we're going to see log
as we go further.
Yes. Log base anything you want. Now, when we're solving equations, you could leave it like this. This is an exact answer. Or you could also find the decimal approximation. We're not going to find the decimal approximation because there's no application here. We're just practicing equation solving. So we're going to leave it like that. And that's what we'll do through these problems. Oh no, here goes. Now it's giving me my message. All right. Number 3. Number 3.
What happened?
I don't know. Right here we have two different bases. And we have variable expressions in the powers. So we're going to have to take ln of each side. Ln of each side. And so if I go, okay, this is ln of 5 to the x minus 2 power, there it goes, equals ln of 3 to the 3x plus 2 power, there it goes, we've lost it. Bummer, it was working for a while. Now it's become cryptic here. I don't know why. Every time I get that message, oh, my recording stopped.
Oh, it went all 1 second.
Yeah, that's a bummer.
Turn around now.
Persistent here. Maybe keep trying. Okay, so we have ln of 5 to the x minus 2 power equals ln of 3 to the 3x plus 2 power. Okay. There's no way I'm going to have enough room on here anyways, so probably turn around. But so are we okay with the first step there? Take ln of each side.
Yes.
The ln accomplishes what purpose for the equation solving here?
Allows you to pull the x's.
Yes. Allows you to pull the x's down. So when I do that, I'm going to write this as x minus 2, and I'm going to place it in parentheses. You'll see why in a minute. Times ln of 5 equals 3x plus 2 in parentheses times ln of 3. All right, so that's what I have so far. Now, this relates to what we talked about on that quiz earlier with the find the inverse of the rational expression. We're going to have to collect all the x terms on one side. But before I do that, you understand ln of 5 is just a number, right? It's an irrational number. If you were to plug it in your calculator, it'll be a decimal value. Fill up the whole screen. My algebra students call that a big number, quote, big number. It fills up the whole screen. I could really blow their mind by saying it keeps going. It's even bigger than you think. Not necessarily big, but it's irrational, but it's just a real number. So I have x ln of 5 minus 2 ln of 5. That's a minus sign there. And then equals 3x ln 3 plus 2 ln 3. So I have some terms that have variables attached and some terms that don't. Do you see them?
Yes.
So I have 4 terms. 2 of them are variable expressions, 2 of them are not. So I'm going to move all the variable expressions to one side of the equation, to the left, and all the non-variable expressions, the constants or real numbers, to the right. So that means along with the x ln of 5, I'm going to subtract over the 3x ln of 3, and I'm going to take the 2 ln of 5 and move it over to the right to pair it with the 2 ln of 3. So I have, hard to convince my algebra students, my algebra 1 students too, that these are actually numbers, but we understand that, right? So I have just numbers on the right, a real number, and on the left I have algebraic expressions with the variable x. And x happens to be common to both terms, so I can factor out an x, and I'm left with ln 5 minus 3 ln 3 equals 2 ln 5 plus 2 ln 3. And I'm really only one step away from solving this. At least to get an exact answer, right? I'm only one step away from solving this. What's the final step? I could do some kind of, I don't want to combine them because I have to change them to decimals. So I'm just going to divide. That's it. Just going to divide each side by ln of 5 minus 3 ln 3. And over here the same thing, ln of 5 minus 3 ln of 3. And so these cancel, leaving me just x equals 2 ln of 5 plus 2 ln of 3 over ln of 5 minus 3 ln of 3. first period we talked about this a little bit. You can actually, using the properties of logarithms, simplify that into further, but we're not going to. We'll stop right there. It looks like you're out of room anyway. And I am too. But that's the exact value of what x is equal to. If you plugged all that into your calculator, it would give you a decimal approximation. Actually, we're going to skip over number 5. It is so similar to number 6 that we're going to skip it. Especially since we already understand that log base 5, ln, they're really, they operate the same way, right? So let's go and skip over to number 6. The number 7 is a little bit different, so I want to talk about that one. But number 6, what we need to do first is get this to be a single logarithm here. So here's what that looks like. The properties of logarithms say that ln of x plus ln of x minus 4 is same as ln of the product of x times x minus 4. And so using the properties of logarithms, I'm going to write that as a single logarithm. So now, because I have logarithms of the same base on each side, I can drop the logarithms and just say, okay, x squared minus 4x must equal x plus 6. And now I have a quadratic equation that I hope is factorable. Because if it's not factorable, then I have to use the quadratic formula to solve for x. So subtract the x over. Unfortunately, it is factorable. I can see it here. It factors as x minus 6 times x plus 1 equals 0. So my two potential solutions, once again I'm calling them potential solutions because I have to plug them into the original to see if they actually are in the domain of logarithm. My two potential solutions are x equals 6 or x equals negative 1. The 6, if I plug it in here, here, and here, all give me positive values. So the 6 works. The negative 1 does not work. If I plug negative 1 in here, ln of negative 1 would give me an error message if you tried to evaluate that. Negative 1 is not strictly greater than 0, so it's not in the domain of logarithm. So you're going to have to check that on each one of these. We'll have to check that on each one of these. All right, number 7. This one's a little tricky just because I have the logarithmic expressions on opposite sides. There is no property that's going to help me combine these two. So what I need to do is move this over to here first. So it looks like this. Log, we're base 10 now, of x minus 16 plus log of x minus 1 equals 2. Now I can use the product law here for logarithms and combine these together. So this is the same as log. Let's go ahead and do the multiplication. I think we can do it. Can you do the FOIL? X squared minus 17x plus 16. Yeah, that one's not too bad. Equals 2. And then on this particular problem, I have a logarithm on one side and a something that's not the same log on the other. So I can't use the tactic I used on number 6, but I can use my definition, right? If I write this in a different color here, here's my 10. So that would mean 10 to the second equals x squared minus 17x plus 16. 10 squared is 100, so I get 0 equals x squared minus 17x minus 84. I hope that's factorable. If it's not, I'm going to assign James to do the quadratic formula. Is it factorable? If you're ready are you ready to jump in and start the quadratic formula yet? He already did it. I wouldn't do the quadratic. I don't want to do the quadratic formula. I hope it's factorable. It is factorable. Oh, okay. So it's 0 equals, we'll do it right here, x and x. Okay, what are the factors then if it's factorable? Yes. Two numbers that multiply equal negative 84 and add equal negative 17. All right, negative 21, positive 4. Hey, that works. That works. Thank goodness. So x equals 21 or x equals negative 4 are possible solutions. Okay, now don't just assume that the negative one won't work. Sometimes it does, but here it doesn't. It would make these negative. So x equals 21 is, you might want to make a note of that. Sometimes the negative values work. Okay, sometimes the negative values, if you plug them in, will give you a positive argument of logarithms. You just need to check them. All right. So that top half was probably the hardest part, I guess. It's just working on solving equations, both exponential and logarithmic. So have some practice on that on the worksheet. Tried not to do too much on there, but there's some practice. Some applications of logarithms and exponentials. We're going to start that today with this is just talking about money problems. Yeah, we've done this before. And then we'll do a little bit more next week as well. But a couple formulas here you need to know. One of them is compound interest. That's regularly compounded interest. Regularly could be once a year. It could be quarterly, like 4 times a year. It could be monthly. As opposed to continuous compounding, which is A equals PE to the RT. We had a shampoo called PERT Plus. That's how I remember it. So it's the PERT equation, the shampoo equation.
That's how you're supposed to remember
It's a shampoo. You don't see it anymore. But what was great about it is it was an all-in-one, and all-in-ones are great for guys. Yeah, I think yeah. So it was bad for your hair, so, but as guys weren't worried about it. Hair falls out, less have to worry about. Less haircuts, more money for parts, motorbikes. All right. More toys we can buy, right? More climbing equipment. Skis. Shampoo and conditioner are expensive.
Yeah, all day, every day.
It is. It's there much faster. You don't have hat head or helmet head when you pull the helmet off. I think I have to take out. I have to take out a second loan on my home for all the hair products I have in my house now. I've got my daughter who's adopted. She's half African American and half Irish.
Oh my God.
She's got the curly hair. She has special shampoo and conditioner just for her hair. It has something with the name Diva in it, which fits her personality.
It's like the old works.
It is. We've researched this. It's very expensive. Yeah, but it's not PERT Plus.
No, you don't like that.
The P, good. Good, guys. A is the amount. I think I have it here somewhere. There it is. A is the, okay. A is actually the amount of money that you get at the end of whatever the cycle is. P is the principal. R is the rate per period, and N is the number of time periods. So P is the principal. In other words, not like Mr. Pryor, but principal would be the amount of money you put in the bank. You put $1,000 in the bank, and it's going to tell you how much money you have after you've applied that interest.
No?
Interest,
Especially at the 2.4%. Compared to like .02.
Yeah, it's not very good right now.
Yeah, exactly. Congratulations, you
Well,
won
yeah.
a penny last year.
Yeah, well, that's just in savings accounts. You have to invest in things like mutual funds.
You have 4,000.
All right.
Yeah, here's another penny for staying with us.
Did you guys do this last year where you looked at what happens as you compound more and more often?
Yes, sir.
I heard, yes. And so,
How to become wealthy in a year.
yes, Mr. Sarge, taught financial analysis at one time, right? Did he tell you that? No? He taught financial analysis, so so he probably gave you plenty of understanding. So we're not going to do all these. Here's the big deal. What happens as you compound interest more often? You get more money. But obviously it's not, you can't just keep getting more and more money. There has to be a ceiling on it, right?
Oh,
There is, yes, there is. Even compounded continuously, it's limited. For example, if in this problem, just jot this down. Okay, you don't need to, we're not going to do this whole problem because you've already done this before multiple times. I think you have, last year they seemed to come with a good understanding, so he must have done this with you. But if you compound the interest just annually, one time a year for 7 years, you end up with $3,777.89. Now, if you do it quarterly, monthly, weekly, that value does what? Right, exactly. Now, if you do it continuously, have any guesses as to how much more money you make? If
It doesn't detect that your computer performance is slow.
He gets 1,000 more, 100 more, a couple hundred more. Okay, good guesses. Any other guesses out there?
More.
Okay, here's what it ends up being: $3,785.40. So, how much more is that?
$10.
Yeah. Yes, $8. So, guys, here's the moral of the story.
Hey, I'll take that $10.
I would too. Banks typically take their interest for the year, their annual percentage rate, and then they divide it by 12, and they calculate the interest once a month. If they wanted to, they could offer, just for fun, continuous compounding, and it wouldn't really make that much of a difference. Although when they have enough customers,
then they'd be losing.
It could, right? So, but you can see that there's obviously a limit on it. These formulas, both are exponential growth formulas. Okay, so that's how it relates to what we're doing now. Let's flip over to the back side here. With calculus, you'll learn via limits where that number e comes from and it's compounded continuously. All right, number 9. It says, how much principal should you invest at 5.9% compounded quarterly? So quarterly would be 4 times per year to return $7,400 after years. Okay, so how much principal should you invest? This is not using what we've been doing so much, and in terms of logarithms, because if I plug into the first formula, so you have your formula, you got to flip back and forth. Let's write it down. The formula is this: A equals P. Well, it's 1 plus R over N. Oh, there it goes. It's just give it a moment. It'll come back. It seems to be coming back.
Whoa. That's a completely different.
No, this is the one I gave you. 1 plus. Oh, okay. You're right. It is.
You can't be doing this, Jimmy, around. Break out.
Okay, write down this formula. Here's why. You remember on the previous page I said I called R the rate per period? Well, just like banks do, over 1 year they're going to divide by 12. So like if you have an interest rate of 3%, it's actually 0.5% compounded per month. So that's what's going to happen here is, go ahead and write this down. The N is And then we need to multiply. I need to add one more in here too. So not only do you divide by n, but instead of taking t years, you're going to have to divide t by n as well. So please, okay guys, just write down the formula here. The n represents the, just listen, the n represents the number of times you're going to compound in that 1 year. Okay, so n equals number of times compounded per year. Okay, so it'll look like this. Let's plug in everything we know. So you're going to need to write this down because the formula I gave you didn't have the n in it, right?
Is it divided by n?
Okay, the one on the previous page did not have the n in it to deal with the number of times.
Is that t divided by n or just t times?
It's t times n. So the a is going to get replaced with what? Okay, just you need to divide the r by n. Here's why. Here's why. Okay, guys, if you're going to calculate your interest 4 times in a year, and your interest rate for the year is 6%, you don't get 6% each of those times you compound it. You have to take 6%, divide it by 4, and that's actually the interest you're getting each time you compound it. Okay, so that's why we're dividing by n here. And then the number of times you get new interest gets multiplied, right? Because over the 8 years, I'm getting, like, I might get a statement every 3 months if it's quarterly with my new interest. So you got to multiply 8 times 4. It's going to happen 32 times. So 32 times I'm going to get a new bank statement with my interest added into my principal. So it's P. We have 1 plus, okay, we can't write 5.9 in for R. It's 0.059 divided by 4 times 8 times 4. Okay, so plug in everything you know. Don't do anything, just leave it blank. Okay, so somebody calculate the 0.059 divided by 4. A lot of times they leave this out in the calculation, but 0.059 divided by 4, what do you get? 0.01475. Okay, so this is P 1.0174. Oh, 0.01475. So 0.01475. So we'll say 8. And then to the 32nd power. That's what 7,400 equals. So change it to that. So then we need to solve this. The 1.0, the reason I took it to so many decimal places is because then I'm going to take it to the 32nd power. So this will kind of save some of the round off there. But P is equal to whatever I get when I take 7,400 and divide it by 1.0148 to the 32nd power. So you should have gotten, here's what I got for P, about 4,631.71. So that's solving for P. So that's solving for the A. Now we're going to switch here what we solve for here. All right. So the next one here, number 10, says you borrow $150,000 at 6.5% interest, compounded monthly, and agree to pay off the loan in 4 years. How much interest will you have paid? Probably did a little bit of that last year too.
$4.
I may skip that one. I may skip over to 11 here. No, you're going to pay a lot of interest. So
No, $4.
no, this would be like for a home loan. If you borrow $150,000 at 6.5, that's a pretty high interest loan, right? Like my interest loan right now was I got a 3.25%, which is good. Usually when the interest rates are low for borrowing money, it's not very good for saving money either, which is what you mentioned before. We're going to skip 10, but do you guys have, you probably talked about this a little bit last year too, especially having Mr. Sarge. Do you realize how much you end up paying in interest on a $150,000 loan?
Too much?
Quite a bit. Do you have any guess? What's it? That's what it ends up being. Yeah, you already calculated. So it's a lot of money. It's like money that's
Almost a half.
You're burning up the money, right? But 40, yes. So if you borrowed $150,000, this is a great lesson in a financial analysis course. You borrow 150 grand to maybe, so you'd have to probably have some money on hand to make the down, as to buy a house. 150,000 probably wouldn't be enough. But at 6.5% interest, compounded monthly, which is what they do, and agree to pay off the loan even just in 4 years, you'll end up paying an extra 44 grand for that.
For that cash.
So you better take that 44 grand and figure out, was it, you have to compare that to what it would be monthly to rent, right? It's a lot of money, so it's something to consider. That would be a terrible interest rate you would just been had. But let's go down to 11. I want to do one where we're solving for the power. Okay, so it says Cheryl invests $400 at 9% compounded continuously. That means we're using my shampoo equation, PERT plus 1. So A equals PE to the RT. And we're going to plug in everything we know. Now, if Cheryl invests $400, what amount will she have in her bank account when she doubles it? 800. So the amount is 800. Okay, if I change that to triple it, which I think I might have in one of the problems on the worksheet, you would have then 1200. Okay. So R is the rate, 0.09 to the T power. So now this is right in our wheelhouse. How do we solve this problem for T?
Oh, I know.
First of all, though, before we ln, divide by 400. So I've got 2 equals e to the 0.09t. Now, the astute student out there would notice I really didn't need to put in 800 and 400. Doubling means you're going to have a 2-to-1 ratio, right? So I could have gone right to this step. If I said triple your money, it would be 3 equals e to the 0.09t. So keep that in mind. Take ln of each side, so we'll do that over here. ln of 2 equals ln of e to the 0.09t. ln of e is just 1, so I have 0.09t equals ln of 2. So t equals ln of 2 divided by 0.09. Now, this, guys, this is a word problem, so it really doesn't make sense till we get in that form. This is how many years to the nearest 10? So I prompted that. It's about 7.7 years to double my money at 9%. No, it's not, no, 7.7 years because it's 7 tenths times 12 months.
Almost 8 months. 7 years, almost 8.
Now, number 12 is the same idea, but with the other formula. Okay, so let me write down the formula again. It's A equals P 1 plus R over N to the, NT here, so NT. Compound core, how many years will it take? Okay. All right. So right here we have A. The amount is 10,000. The principal is 4,000. We have 1 plus 0.08 over 4 times nt. Now, 4t I should say. T, because n is 4. Could somebody calculate this right here? And remember, order of operations says take it to the exponent first before multiplying. Don't multiply 4,000 times this number. It's not, you can't do that. What's 1 plus 0.08 over 4? 1.202?
No, 1.02.
Oh, okay. 1.02, yep. To the 4t. And then over here, if I divide by 4,000, I lop off 3 zeros. 10 over 4 is the same as 5 over 2, right? Am I ready to do ln of each side now? Yep. So it's ln of 5 over 2 equals ln of 1.02 to the 4t. And then we just solve that. Bring the 4t down. So 4t ln of 1.02 ln of 5 over 2. So 4t equals ln of 5 over 2 divided by ln of 1.02. So we're just taking the ln of each side. Or you could take log base 10 of each side. That brings down the 4t. Yep, take all that and then divide by 4. Save your time, yep. What's that? 11.6 years is what that ends up equaling. Yep, 11.6 years. So you are going to be asked to solve just a couple equations where you have to solve for the variable power. This is just one page, 10 problems. I know. That's the generic formula. What are you doing your time? So is that formula? What's that? That's called simple interest, or the discount. You really have to divide by n and multiply the power by n. Most loans and banks are all monthly. So you're almost always divided by 12.
We're gonna have stuff so
Yeah.
The font is
You might want to try number 5 is a good one to try. Maybe number 10. You can figure out the one that you really want.
Yeah, and now there's
no. Yeah. It better not be Tuesday, Wednesday. No.
This next week. Oh, and afterwards, don't do stuff like why don't we like
Next week?
not next week?
The next week.
Yeah.
I think it's Tuesday, Wednesday.
Alright.
Or maybe Wednesday, Thursday.
Why is it the 5?
Because you're trying to scare me, that's why.